Swayam Prabha. Digital India. Educated India.
Welcome back to real-time digital signal processing course. Today we will be discussing about module 2 unit 7 FIR filters. So, as a recap, we saw in the module 1 which goes from unit 1 to 6 introduction, design concepts and real-time constraints what we have considered. In this class, in the module 2, first we will discuss about digital filters and later with FIR filters. So, why do we need digital filters? So, where we are going to use it in signal processing for separation of signals is one of the application we say. As you can see in the example here, your original signals has multiple frequencies components present in it, and you can see that how they have been added and each one how we can separate it from the signal using different techniques. So, we will be seeing in a while. Here it is low pass filter, this gives the high pass filter, and this is band pass, and this we call it as notch filter or band stop filter. If only one frequency has to be removed, then we call it as notch filter. The one application is restoration. So, from these signals I want to reconstruct my signal, then as you have seen the thing, we will be adding all of them and I will be getting back the original signal. So, if I want to restore back, I will be using that. When coming to analog, that is electronic filters can be used for these same task. However, digital filters can achieve far superior results. So, we will see in a short while how it is going to be done with digital filters. And the application of digital filters is given here. One is in the signal processing what we are considering it. It can be in the communication systems or in control or in electrical systems or in biomedical systems. Everywhere we need the filters. What are the advantages of digital filters? So, we know that many input signals can be filtered by one digital filter without replacing the hardware, and then they have the characteristic like linear phase response. We will see it in a while, and the performance does not vary with environmental parameters. So, if you are in a cold place or is in a hot place, as we know in the analog filters, their components have to be highly meant for those conditions. If it is not, the environment is going to play an havoc. Hence, digital filters will not have this degradation for environments, and that is what it says. And it is unlike analog filters, these can be portable. So, from place to place and from one application to the other application. The other disadvantage of digital filter is basically the bandwidth of the digital filter is much lower than that of analog filter, and we are going to have quantization noise in this filters. The accuracy of digital filter depends on the word length used to encode them in binary form. So, we have seen the number system. So, we have used fixed point and then floating point. So, their pros and cons. So, this will be constituting whatever we say that accuracy is going to be affected, and it requires more design and development time compared to analog filter. So, one has to see what should be the order of the filter, whatever you are designing, and then you have to pass through input and then if it is available and then see, and it is going to take more time. The difference between analog digital filters is this. The main difference we will consider here, two methods, is that digital filter circuit has to sample the analog signal first and convert it into a set of binary numbers. And in contrast, analog filters need not have to do this conversion, they can be used directly wherever it is required. So, coming to some of the recent in the social media, what kind of filters is being used is shown here. So, most of you may be using this. Augmented reality filters are computer generated effects, all of you know about it. So, they are layered over the real life images in your camera displays. And in Instagram stories, so you will have most of this augmented reality filters. They alter the image of your front or back camera displays. You can think of Instagram's face filters, how they will be working, and then you can imagine what is the role of filters in social media. Coming to noise filter, digital noise filters, why we need it? In basically in smart TV, it is going to reduce the analog noise that is created during your signal transmission. Helps in eliminate excess noise in a picture and reduce your flickers caused by them. And how we can eliminate noise on an FM receiver. So, you will be knowing that frequency modulated receivers most of the time what we will be using it. How we can eliminate the noise in that? Usually keep any cell phones or two-way radios at least 20 feet from an FM receiver. And then in cell phones, even when not in use, all of us know that send out pings that are picked up by your FM receivers. You can choose a station and adjust the dial to the setting if you are using an analog radio. Add a large external antenna to the receiver. That is how you will be eliminating your FM receiver noise. So, in other way what we will see noise is in your microphone, basically whatever microphone you are using for your applications, they will have some what we call it a static noise. So, how you can eliminate the static noise? You can unplug and replug in your mic. That way it will try to adapt to the noise which is present there and then it can eliminate it. So, other way of doing it is try unplugging your headset or standalone microphone from the computer or device to which it is connected and then replugging it back. So, if possible try using a different USB port. If it is USB connected, you can try on a different USB so that your static noise is gone. So, if there is a hissing noise in the audio, all of you know the thing, then use low pass filtering to avoid this hissing noise. And then how we are going to stop my mic from picking up background noise? Here it was the static noise, here background noise, because you will be at different places. How you can do that? So, what it says is click the recording tab in the sound window and select your microphone device and click properties, click the levels tab. So, in that what you will be doing is background noise, try lowering your microphone boost option. Perhaps if you have kept it to 20 dB, try to reduce it to plus 10 dB. So, the other one is we know that most of the ECG signals carry line frequency in them. How to avoid the line frequency? In that case we use the notch filter to eliminate this line frequency. So, usually in abroad it is 60 hertz or USA, and in India we call it as 50, whatever our line frequency is 50 hertz signal. So, we will see today FIR filter. So, first we will see why we have to go for FIR filters, their advantages and disadvantages. So, the advantages as it is listed here, so we say it is stable, simple, and design complexity gets really linear in this case, and then it has a linear phase response, we will see in a while, and it is easy to optimize on the order of the filter what we want to have it, and this is a non-causal system. Hopefully you would have done your causal and non-causal systems earlier in your signals and system. So, how to make non-causal system into causal, all of you must be knowing it, and it has a transient which is going to be finite duration. So, what we call it is, for finite input the output is going to be finite. So, that is why there will not be any transient which is going to be finite in this case. And we know that quantization noise is not much as a problem. So, this is one of the advantage of our FIR filter. What are the disadvantages? So, we know that the order of the filter we usually call FIR filter is equivalent to an open loop systems. It requires large storage basically. So, it needs storage requirements what we say, and then cannot simulate prototype analog filter. So, a IR filter, infinite impulse response filter, we will be taking it in further classes. So, we know that most of the design is done in the analog domain and then we convert it into digital domain, because the earlier world more than 100 years analog filter have survived and then they are very well working with the system. But whereas this FIR filter we will not be able to simulate using our analog filters. So, for implementation complex computational we say is techniques are required. So, and then it is expensive due to a large order, we have to pay in for the memory as well as the speed of it, and then it is hard to implement than IR filter. We will see how we will design it in the lab class, and it is expensive as it is large order, it is cost is going to be more, require more memory and time consuming process, because we are talking about real time. So, if the order of the filter is very high and then we are unable to complete within the next sample comes, if it is interrupt driven, then we will be losing the sample. That is why they are very time consuming in the case of FIR filters. So, we will see that how they can be used, they are represented in this figure. So, we will consider FIR filter of length m order, what we call it. So, then what we say is order of n is equal to m minus 1. So, you have to watch out, it is that is order minus number of delays what we will be considering as the length of the filter basically. So, we are given the equation y of n is given by k is equal to 0 to m minus 1. So, bk into x of n minus k, x is our input, bk is our coefficients. So, same thing we said that it is equivalent to convolution if it flashes to you, h of k is the impulse response what we take it, and x of n minus k is your input. So, we can represent it in this way, but since we use the filter coefficients, usually we represent it as bk. And how in the flow diagram we are going to represent, x of n is the input. So, these are the square brackets are the unit delay basically, and then x of n is multiplied by the b naught coefficient, and this is the result what is available for our adder. Same way here, the after the delay which is going to come, so output is going to be x of n minus 1 into, if I consider it as b1, then this is going to get added with the previous one, so on, because we are going to have m minus 1 delays basically. So, the last one is going to be bm into x of n minus m will be the thing, whatever the order of filter m, which is going to be multiplied with your bm coefficients and added together, you will be getting y of n as the output. So, continuing with the thing. So, if we represent our input as a impulse response, if I want to take it, then x of n is going to be delta n basically. then we will be getting the what will be the impulse response of the filter, we will be getting it. So, as h of n is equal to what we call it, h of n is the impulse response, which is equal to y of n, which is given by k is equal to 0 to m minus 1. So, you are replacing x of n minus k with the impulse response delta n minus k into b k. So, the output is going to be b n, what you will be getting, n will be varying to 0 to m minus 1. So, the impulse response is of finite length m as required, and then note that FIR filters have only zeros, as you can see from the thing, they do not have any poles. That is the reason why we call this filter as a stable filter. So, or this name is all zero filters also. FIR filter is also known as feed forward or non-recursive or transversal filters, what we call it. That is, as you can see in the previous case, the output will be only going in the forward direction, that is why it is a feed forward filter also. Coming with the design aspect of it, some of the parameters what we have to look in. The characteristics as specified in the frequency domain in terms of desired magnitude and phase response of the filter. We call it as h of omega in the frequency domain. So, the filter design involves determining the coefficients of our causal FIR or IR filter that closely approximate the desired frequency response specifications. So, what are the design specification is given with this diagram. So, what y axis represent is the magnitude of h of omega, and then x axis will be represented with omega, which varies between, in this case, 0 to pi what has been considered. Most of the time it will be minus pi to pi or 0 to 2 pi, but we will be interested in only 0 to pi frequency components present in the thing, as our sampling frequency is twice that of the highest frequency. So, highest frequency is represented with 2 pi, hence we can consider the frequencies that are present only up to pi. And then we say omega is the pass band frequency, that is from 0 to, if here it is the example taken as a low pass filter. So, I want to allow all the frequencies which are in the pass band, that is WP, where I want to stop the collecting my frequency components. Then what I have is I am going to say stop band. WS is going to say where I have to stop my collection of components. So, that is WS. Between the difference between our WS and WP, we call it as transition band. For most of the cases, we want direct dropping down, which is not going to happen, we will see in a while. It is going to be a smooth transition what it should happen. So, which will be constituting for our transition band. And then we say that is WS is my pass band edge frequency and WS will be stop band edge frequency. And what are this variation I am going to have it. Most of the cases I want the magnitude to be 1 basically, but we know the constraints as and when more constraints are put, our design is going to become very critical, then we will be having order of the filter very high. So, as we little bit relax on some of the components, so we can have the order low. So, we say that delta r is the my ripple what I can allow actually in the passband region between minus 1 minus delta r to 1 plus delta r. So, then passband will have little bit of ripples in the passband, and then I can little bit deviate from that. And how I am going to represent the stop band, although most of the cases I want the flat response which may not be able to achieve it. So, I have to specify what is the dB, that is stop band attenuation, what we call it as delta s, how much I have to come down so that I will not have the frequencies beyond this region WS. So, coming to comparison between FIR versus IIR. So, we will take up IR filter a more detailed one next few classes. What is the comparison? We say that FIR filters are normally used when there is a requirement of a linear phase. So, we will take it up a little more in detail in a while, and FIR filter with the following symmetry, what we call it as linear phase. What is that symmetry? My impulse response has to be h of n equal to plus or minus h of m minus 1 minus n for n is equal to 0 to m minus 1 order of the filter. Whereas in IR filters, they are normally used when linear phase is not required and cost effectiveness is going to be needed. We say that they have compared to FIR filters, they have lower side lobes and then stop band than that of FIR filter, and for the same type of design we will see it later also how it is going to, we will be meeting with IR filter with a less number of coefficients. In some phase distortion is tolerable, then better to use IR filter implementation at fewer parameters requiring less memory and then lower complexity. Coming to how we are going to design FIR filters. So, we say that we cannot derive it from analog filters. So, we have to design in a different way. So, why we have to bother? Because we know the advantages of them which we have already discussed, and then how they are going to achieve linear phase stability, and then how they will have the magnitude response changes what we can accommodate, and then it is easy and then convenient to implement. So, coming to the linear phase. So, what is it? The ability to have an exactly linear phase response is the one of the most important of FIR filters. What is that? H of omega, it should be equal to magnitude of h of omega into e power j phi omega, where phi of omega is nothing but minus omega n naught. So, when general FIR filter does not have a linear phase response, but this property is satisfied when your h of n is equal to plus or minus, if I have taken h of m minus 1 minus n, n is varying between 0 to m minus 1, definitely we will have a linear phase filter. So, different types of impulse response, whether it is odd or even, and then as you are seeing it, there are 4 types how it can be designed. So, you can go through them, and then whichever is convenient you can select one of them to design your linear phase FIR filter. So, why do we say it is linear phase? The phase is a straight line in the pass band of the system. As you are seeing it, this minus pi to pi, I say that that is my pass band. It should be linear, or we call it as all pass system basically. In this case, group delay is given by the negative of the slope of the line. So, we will see it in a while, hold on for little while. So, coming to the other thing, we said all pass system because we may have discontinuity in the filters or band pass filter at different frequencies what I want to design it, then what is the thing is going to happen? We say phase wrapping may occur, that is what you are seeing it. So, but the phase is still considered to be linear. Why? This is the passband region of one this thing parameter, the other region of the thing is from here to here, still we have a what we call it as a line is linear in this case, and then here this side also. Coming to the other part of it, that is if we are considering the high pass system, we call it as high pass filter, that is the low frequencies are going to be eliminated, only higher frequencies are going to be considered. In that case, the phase response looks like which is having a discontinuity, that is from here to here I will be having, that is my pi to magnitude 1 in this case to pi, and then from here it is minus 1 to minus pi magnitude if I am considering the magnitude as minus 1 to 1. So, then here it is going to be linear, and then this side also it is going to be linear, both on the negative side as well as the positive side of it. So, the other one, as you can see the thing, when we say it is going to be linear phase. So, this is my passband region. If it is going to be linear, I say it is linear phase, and I am not bothered about beyond my interest of region, they are not linear, they become non-linear in phase. So, some of the terms we will see it which is going to help us for our linear derivation. So, discrete time Fourier transform, some of the theorems and properties which more we will be taking it up when I consider DFT and then FFT. So, the property we consider is the notation what we are going to have it. In time domain we say x of n, x1 and x2, and frequency domain all of us know it is capital X of omega, x1 of omega and x2 of omega. So, when we say it is linearity, so when it meets the superposition theorem, so which is both commutative as well as can you guess the other one? So, a1 into x of x1 of n plus a2 into x2 of n when I do the thing. So, I should be able to get even in the frequency domain a1 into x1 of omega plus a2 into x2 of omega. So, when we do the time shifting, that is if I provide a shift of k n minus k, then here the resultant is going to be e power minus j omega k into x of omega. In the case of time reversal, x of minus n will be giving me in the frequency domain is capital X of minus omega. So, when we do the convolution of two signals x1 and then x2, I know it is convolution in the time domain, whereas in the frequency domain it is multiplication. So, when we want to do the correlation, basically it can be autocorrelation, as we will be seeing it later, or x1 to x2. So, if we consider the thing, this is in the time domain it is convolution, whereas in the frequency domain it becomes a multiplication with respect to complex conjugate of the other sequence. So, if we consider x2 of n as real, it becomes a multiplication of x1 of omega into conjugate of x2 of omega. So, whereas in the some of the Wiener filter we will be considering in the adaptive filter LMS algorithm. So, that time your autocorrelation with respect to the same signal what you are seeing it, that convolution of this, that is a time reverse signal what you are having it, which becomes the square of the x of omega, magnitude of it what you are seeing in the filter domain. So, there are other more properties, and then both in time domain and frequency domain. So, you would have studied in your signal processing or signals and system classes, you can look into them. So, now we are telling that linear phase. So, what we have said is something group delay which we have to consider. So, y of n is my output, and then x of n is going to be delayed by n naught. So, we call that as group delay. Then what happens to the frequency domain signal, which is y of omega is the output, which is going to be x of omega, you are seeing e power minus j omega n naught it is going to be. So, then what happens to the magnitude and then phase responses basically. So, h of omega will be y of omega by x of omega, which is going to be given as e power minus j omega n naught, and the phase of it we call it as phi of omega, which is going to be minus omega n naught, and because we know that n naught is the group delay, which is minus omega into group delay. So, in general, even for nonlinear phase systems, we consider group delay as the differentiation with respect to our phase. So, that is minus d by d omega of phi of omega, negative part of it what we will be taking up. So, continuing with the group delay. So, we know that linear phase filters maintain the relative positioning of the sinusoids in the filter pass band, as you will be seeing it, that is structure of the signal while removing unwanted frequency components. So, we see that some of the this is an input, and as you can see this is a low pass filter which is represented both in the negative domain as well as in the positive domain. So, the phase is going to be linear in this. So, output after passing it through also you will be having a little bit delay at the output, but they will maintain the same phase of the thing. So, why do we need a linear phase? So, as you know that in what happens to loss of phase information, that is one of the thing whatever literature gives it. Most of us, how do we identify the faces of people basically? So, we say that the phase for one person to the other person is different. So, if their linear that is a passband frequency range linear phase or close to linear phase is required, otherwise I may be reconstructing a different one, as you will be seeing it, some of the frequency domain component how it looks like, and then what is the phase of it what you are looking at it, and if they are distorted, then you may not see the same phase, you may be looking at different phase. Okay. So, linear phase FIR filters, as we said, how we can develop them, that is we follow the symmetry property. So, in this case we will be following only the simple one, we will assume that h of n is equal to plus or minus h of m minus 1 minus n for n varying between 0 to m minus 1 what we will consider. That means what is the thing? So, I am considering the positive side of this for these values as well as h of n for the negative of it what I am considering it. So, we will see that what happens if I give delta n minus delta of n minus 1 as my impulse response to my system. So, whether it is going to represent a linear phase or not, we will see the thing. So, for that we have to see the phase response as well as the group delay. So, note in this case, because m is equal to second order we have chosen the thing. So, it will be going h of n will be equal to minus h of 1 minus n, which is equal to h of minus h of m minus 1 minus n. So, these are the two things what we will be substituting. First, n is equal to 0 comma 1 because m is equal to 2. When n is equal to 0, h of 0 will be minus h of 1 minus 0, which is nothing but h of 1, and when n is equal to 1, h of 1 will be is equal to minus of h of 1 minus 1, which becomes minus 1 basically, which is h of 0. H of 0 is 1, so it becomes minus 1. So, this is how you will be representing with respect to n is equal to 0, it is impulse response is 1, and then when is equal to 1, its impulse response is minus 1. So, we will see an example how we are going to show that this has a linear phase. So, what is that? Equivalent to convolution of your x of n into h of n by expanding the our function, which is nothing but x of n into delta n plus delta of n minus 1. In this case, we have assumed minus delta of n minus 1. So, this will be negative x of n into delta of n minus x of n into delta of n minus 1. So, which is nothing but x of n minus x of n minus 1. This we call it as first difference system. So, first difference system, what we can go into the discrete time derivative. So, we define this as a high pass filter. We will see it in a while how it can be a high pass filter. So, we will be expanding this. We have h of omega is nothing but n is equal to minus infinity to infinity. This is our DTFT equation, h of n into e power minus j omega n. So, I am substituting h of 0 as 1 and we have e power minus j omega naught plus minus 1 into e power minus j omega 1, which is nothing but 1 minus e power minus j omega. So, when I expand in terms of my exponential, so you will be seeing that simplifying it, it becomes e power minus j omega by 2 into 2j into sine omega by 2. So, this is what if I move 2j into the first place and then put e power minus j omega by 2 into sine omega by 2. So, for various value of omega between minus and pi, if you plot the thing, so you will be seeing the curve like this. So, that means to say low frequencies whatever they are there, that is going to be eliminated. Only higher frequencies, almost when it becomes 1, you will be allowing those frequencies to be present in the system. So, how we are going to consider the group delay? We have to say phi of omega, what we have got it as angle of 2j into e power minus j omega by 2 into sine omega by 2. So, by putting them, that is angle of 2, we know that it is 0, angle of j is equal to pi by 2 and angle of e power minus j omega by 2 will be minus omega by 2, and for sine omega by 2 it will be in this range. It is going to be 0, 0 less than omega less than pi, and it will be pi for minus pi to 0. So, when we put it in terms of omega, which will be pi by 2 minus omega by 2 and 3 pi by 2 minus omega by 2 minus 2 pi in this range. So, when you put this simplified one, you will be getting it as minus omega by 2 into the other one, it is in the range 0 to pi, minus pi to 0 will be minus pi minus omega by 2. So, now we will see that how is it going to be represented. So, we have phi of omega. So, we will be put omega 0 to pi, then you will be seeing this is shown as pi by 2 to pi here, the magnitude is going to be half here, which is going to go between the two, that is pi here. So, whereas in the case of negative region, so you will be seeing that minus pi to minus pi by 2, because we are representing even my y axis is in phase of the thing. So, which is going to be minus pi by 2 to pi by 2, fine. So, how we are going to say that group delay is going to be constant in this case. So, I am going to take the derivative, the negative derivative of my phase. So, which is nothing but half minus pi into delta omega. So, which is going to give me half and then minus pi into delta omega, which omega equal to 0, and wherever omega is not equal to 0, it is going to be half. So, we consider in the passband region, because I am not bothered about when omega equal to 0. So, we know that in the passband region it is becoming constant. So, we say that the delay is constant, or we call it as a linear phase basically. That is the reason why you will be seeing that it is pi by 2 to minus pi by 2, what you will be seeing a linear slope of the line here. So, coming further with the example. So, what we have is this is an assignment for you to work it out. We showed that the FIR filter for a high pass filter is linear phase. Now, it is your time to show that the low pass filter, that is you have been given delta n plus delta of n minus 1 is my impulse response, that this also is a linear phase. Okay. So, you can consider here also you have m is equal to 2, and these are the values what you have it. When n is equal to 0, it is going to be 1, and then when n is equal to 1, it is a plus h of 0 which is also 1. So, you will be seeing that both of them are 1, you are supposed to show whether it is linear phase filter. So, as you can see that when you are giving your delta n representation, input y of n is nothing but because we have a impulse response delta n and delta n minus 1 equal to 1. So, the output y of n will be equal to x of n plus x of n minus 1. It is the scaled averaging system what we call it. So, the averager is also represented as discrete time smoother and we call it as low pass filter. So, some of the techniques to design our FIR filter which we will be taking it up more in our lab class, just to give a flavor of it. So, I can design a Hamming using the window technique. There are different ways of doing it. So, most of the time we will be using MATLAB FDA toolbox with the older versions and latest version use the filter design toolbox. So, here it is the Hamming window what you are seeing m is equal to 16 what we have considered in this case plotting these figures from the MATLAB. So, you will be seeing that this is a smooth as you will be seeing between 0 and the other thing. So, whereas the Hamming window, so you will be seeing there is a little drift in the thing and then that is how what it will be represented. Use a Blackman window, as you will be seeing that it will be having the passband is an arrow band, whereas it is going to drop down the dB whatever frequency response what you can see that is if we have put this as a reference line. So, which will be below this line that is minus 20 dB point, whereas in the case of these are the side lobes what we call it, whether I want a narrow this thing passband lobe or more ripples in the side lobe what we have to take it into considerations. So, for the Hamming window you will be seeing that it goes little more than minus 20 dB, whereas in the Hamming window also, but it is going to come down as you will be seeing when you are using the Hamming window. Most of the filter equations will be using the Hamming window to design FIR filters. So, that is this table shows that how they are represented. The main lobe is going to be 4 pi by m, which is equivalent to minus 13 dB what they will have it. And if I consider the peak 20 log 10 delta side lobe, so it will be coming down to you will be seeing that minus 21 dB, whereas in the Hamming window it comes to minus 44 dB. When I want to go with increasing the order of the filter, basically if I want to achieve it, m has to be increased and then I can go up to minus 53 dB maximum in the Hamming window. And if you consider the Blackman window, I can go up to 74 dB from 58 dB. So, some of the design if you want to have a peak side lobe as minus 13 and other things, you can select any one of these windows. And if you want a variable, you would have heard of Kaiser window, which you can select it, which one of the parameter what beta parameter what you can vary alpha and beta parameter there and select your own window. So, this gives you a flavor of FIR filter. So, in the next class we will be taking up pipelining and parallelism for low power, how we can design these FIR filters. Thank you for your listening and then happy learning in this course. Thank you.